Welcome back to Anatomy and Physiology with me, Mr. Hamele. Today we are going to look at part 2 of our notes on the skeletal system, and we're going to focus mainly on the external and internal structure of the bones, both at the macroscopic level, the level you can see with your own eyes, and at the microscopic level, the stuff we can see through the microscope. Let's get started. So, gross anatomy of the bones, bone textures. There are two main types of bone textures. There's compact bone, which on here we can see on the outer edge, right here, where it's dense, it looks solid. And then we've got the spongy bone on the inside, which looks less dense, kind of porous. It kind of looks like a sponge, even though it's hard. Got a bone here, cow bone, that has been cut open so we can see that. We can see the compact bone here. This is what we see when we look at bone generally. Compact bone on the outside, and then down here, it's spongy bone. And I think you can hear that it is hard. It is bone. So we can get that to focus. Kind of. That is bone, but it is spongy bone. It's got a lot of porosity in there. Okay, and what that does is the compact bone is really, really strong. No ifs, ands, or buts about it. So when you need a lot of strength, you're going to have more and thicker compact bone. But that gets really heavy. If we made our bones solid compact bones, they would be super heavy, which means we need a lot more energy to make them, a lot more materials to make them, a lot more energy to move them. So we got to find the balance, as with anything in biology, right? You can make it super strong, but if it's so heavy you can't move it, what's the point? So we put this spongy bone in here. Okay, it's kind of like the cross supports on a bridge, you know, those girders that help hold it up. Okay, it's stiff, it's strong, and it lends a lot of support in different directions without adding a ton of weight. So you can make a really strong bone that's actually relatively light. And we're going to play around with that when we get to the lab, where you have to bioengineer your own bone and try to maximize the strength versus weight component of it. This is the kind of key stuff you're going to have to remember. Compact bone versus spongy bone, and they both serve a purpose. The structure of the long bone. So long bones consist of diaphysis, which is the long part in the middle, and the epiphysi, which are the two ends. So epiphysi or epiphysis, that's an epiphysis together, they're epiphysi. They start with letter E, and they are the ends of the bones. That's how I remember it. Epiphysi, E means end, diaphysis is the middle. So diaphysis is the tubular shaft that forms the long axis, right down here, number 2 in this diagram. It's generally got compact bone on the outside. You can see that here. And then for a good chunk of the middle, it's got a medullary cavity, this hollow space where bone marrow will sit. We'll talk about bone marrow a little bit later, but that sits in this area. And then we've got the epiphysi. Oh, no, that's on the next one. And then we got yellow bone marrow. Fat is contained in the medullary cavity. When you're an adult, when you're a baby, it's something called red marrow, which is important for making blood cells, which we'll hit later. But this is yellow marrow, which is mainly fat storage. And this is why large carnivores have big molars in the back and a strong bite force, is so they can crack into these bones to get to that marrow. That stuff is like candy. Okay. If you look back at ancient human archaeological sites, anthropological sites, you'll see a lot of bones cracked open, and they're trying to get to that marrow because that'll stay fresher longer. It's very energy dense because it's mostly fat, and it tastes pretty good too. Our bodies crave those energy dense type materials, and so our ancestors were looking for that. The epiphysi, the ends of the long bone. Exterior is compact bone, so it's hard and dense, but it's not as thick as the compact bone down here because the stresses are more distributed up here. So the inside is all the spongy bone. You can see how the compact bone thins out as it comes up here. Then the spongy bone is what's going to take a lot of that force and distribute it around so we have an even distribution of forces. The joint surface right here, It's difficult to see on here, but you can kind of see where it's bone, and then there was haline cartilage here. Okay? And haline cartilage, if you remember from the histology unit, under the microscope, it looks like smooth, hard plastic, and it kind of feels like that. It's really good, like friction reducer between the bones. If you had bone on bone, that's like rock on rock. It's going to grind away. You're going to get bone dust. The bones are going to wear away. You're going to get arthritis. It's going to be very painful. But if your cartilage is in good shape, it's kind of like bronze bearings or bronze bushings in a piece of machinery. Those slightly softer, smoother materials, which are lubricated. We learned about synovial joints and synovial fluid earlier in the year. That lubrication is going to help keep them sliding past each other so we don't get so much friction. There's an epiphyseal line that separates the diaphysis from the epiphysis right about in here and in here. Can't really see it on this picture. Do you know what probably the more common name for the epiphyseal line is? Yeah, it's the growth plate. We talk about how the bones grow. They're going to grow at that growth plate. That epiphyseal line, when you're younger, is made up of cartilage and eventually gets replaced by bone when you're done growing. So let's take a look at the images here. So here we got a long bone, diaphysis here and here, epiphysi here and here. We can see we got compact bone on the outside of the diaphysis, and then we got yellow marrow on the inside in the medullary cavity. Then up here we've got slightly thinner compact bone, spongy bone on the inside, so that it's still strong, but lighter. The outer part is covered by cartilage, articular cartilage, or specifically haline cartilage. Here's the epiphyseal plate. Now this is fully bone, so that means that this is a bone from an adult. And we can see that cartilage over the top of the bone down here in the bottom part, if the thing gets out of the way, is where the bone joints kind of rub up against each other. And here we can see kind of the difference at the microscopic level between the compact and spongy bones. And over here, we can see that it's covered by this really tough membrane called the periosteum, and attached to, if I move this out of the way, Sharpie's fibers here attached to the bone. It's really hard to get off the bone. If you ever get a chance, you get a piece of meat that's got the bone in it. When you get in there by the bone, kind of pick that periosteum away. It's really held on tight, and it's kind of what holds the blood vessels tight to the bone, provides a little extra support if there's a break, makes it a little harder for the bone to, can snap, but it's less likely to come off and go like that because it's got that really tough fibrous membrane around it. Let's see. Now here is the structure of a flat bone. Got compact on the outside and spongy bone on the middle. Bony membranes. Yeah, whatever. We'll leave it down there. Already talked about periosteum, double layer protective membrane, lots of nerves, blood, lymph vessels that help to get nutrients and waste in and out of the bone. And there's little holes in the bone called nutrient foramina or foramen. Foramen in bone language means hole, like the big one here at the bottom of the base of your skull where the spinal cord goes into your brain. That's called the foramen magnum, which literally means big hole. Foramen hole, magnum big, big hole. Scientists are really creative with their naming. It just sounds fancy because we use Latin, but that is the big hole. And then, like I said before, it's secured to the underlying bone by Sharpie's fibers. Come on. There we go. So, hematopoietic tissue or red bone marrow. I mentioned this briefly before, but hematopoiesis, that's a fun word to say. Why don't you just pause the video for a second and say hematopoiesis. You really got to move your mouth in a fun way. It's one of those fun ones to say, like endoplasmic reticulum or hematopoiesis. Poiesis is fun. You just gotta have some fun with it, guys. It's one of my favorite ones to say. But hematopoiesis happens in red marrow, and it produces our blood cells. And we're going to really get into how hematopoiesis works when we get to the cardiovascular unit. But I do want to mention where it takes place here in the bones, since we're in this unit. Now, in infants, it's found in the medullary cavities and all areas of spongy bone. So it's found in the spongy bone, but also in the medullary cavity of the bones. It's all red marrow when they're baby. And you can see that down here in this image, all red marrow. In adults, Okay, it's found in the spongy bone of flat bones. So you can see in the skull and the ribs and the hips here. And the head of the femur and humerus is where you're going to find most of that. So if you ever go in to donate bone marrow for somebody who needs it, who needs a bone marrow transplant, or if you need a bone marrow transplant, they can go in right here. They often go into the hip, and they can take out a sample of your bone marrow from the hip, the red bone marrow, so that they can transplant into somebody else to help them make new blood cells. First, they have to kill all the red marrow in the person who's getting the transplant. So that can be really rough and really dangerous, because if you do that, they're not making new blood cells and they're not making white blood cells. Their immune system goes down the tubes, basically have none at that point. So they got to be pretty quick and on top of getting that transplant happening and hoping it takes. So it's a painful procedure, but it's relatively harmless and straightforward to donate bone marrow, and it can save a life. It's not like you're living without a kidney. Your bone marrow will grow back and be just fine. So if you get the opportunity, highly encourage you to do it. All right, so let's take a look at the microscopic structure of compact bone here. So there's a number of things to point out. Let's move myself in here closer. So here we're looking at a cross section. We can see they're basically the structural unit of the at the microscopic level is called the osteon. It's like a pillar, okay, or a column in your bone. You see the circles running up and down or in the direction of force. So pillars work, you push down on here and they're really strong. You wouldn't want a pillar like that. It would be pretty weak. So it's up like this is the osteon. It's like a whole bunch of pillars stuck together. Now, in each of those osteons or pillars, you can see there's a central canal or Haversian canal, which is where the blood vessel goes, the main blood vessel that's supplying these cells with blood, nutrients, and getting rid of their waste products. Now, if we take a closer look in there, we can see that it kind of looks like the characteristic bullseye pattern that we saw in the histology unit. That bullseye pattern is made by different lamella, okay, or layers. If you've heard of laminate flooring, or plywood is a laminate of different layers of wood laminated together. Lamina just means the layers stuck together. But we can see we have these. Here's where the central canal is, Haversian canal. Then we got one lamina, another lamina, lamella here and here. Those are the different layers of the bone that form that characteristic pattern. And within that, we can see these little caves, little dark spots over here, where the bone cells sit. Those little caves, we remember from histology, are called lacuna. If you remember, I sang a really bad song about lacuna matata, ain't no passing craze. It's the caves and bones where bone cells spend the rest of their days. I'm not going to try to sing it again, but here we got the lacuna with the bone sites, the osteocytes in there. And then between the different layers, so that nutrients can get from the blood vessel to all these cells, we have these little cracks. That's not a bad thing. They're there on purpose. They're called caniculi or caniculus, like canal. They're little canals that allow nutrients and fluids to move back and forth between all these cells. So we have the extracellular matrix of the bone and then the cells of the bone itself right there. So is there anything else I want to point out? You can see it transferring over to spongy bone here. We can see the periosteum and Sharpie's fibers over here. All right, now let's get some of the stuff I just talked about into your notes. So move me out of the way. So the Haversian system or osteon is the structural unit of compact bone. Those are the columns we were talking about before. And they're made up of lamella, or different layers of matrix, composed mainly of collagen fibers and calcium phosphates. So calcium phosphates in the bone, that's what you're seeing here in this dead bone. Okay. The calcium phosphates stick around. It's almost like rock, like limestone. So that's the calcium here. Now, when this was alive, and for quite a while afterwards, there's probably remnants of it in here, but it does eventually decay away. There were collagen fibers. And what that does for the bone strength, it's kind of like the calcium fibers, it's almost rock, or the calcium phosphates, almost rock-like in physical resistance to stress, or concrete, right? Concrete is really good at compression. You can put down a lot of force right here on concrete and it won't crush. That's why you can have, giant semi-trucks rolling down the highway at 75 miles an hour and not damaging the concrete surface at all, because it's really crush resistant. But when you go to make a bridge like this and you put your forces here, if that concrete doesn't have any rebar inside of it, or little metal bars running through the center of it, it's going to snap like a twig. It's fairly brittle in tension. Okay, tension would be the bending forces, okay, or the pulling forces. Okay, so it's brittle in that direction. So we need to make a composite material. So we got the compression resistance of the concrete, the calcium phosphates, and we've got the ability of the collagen to bend without breaking. Okay, just like the steel rebar in bridges and things like that, or even in your driveway, you probably have some steel rebar in there if you got a concrete driveway. That steel is able to bend without breaking, and the two materials together lend each other aspects of their physical structure, so that we have a final product which is both resistant to crushing and bending. Okay, so that composite material, and we've got that going on in bones. Something else to think about when you are building your bioengineered bone later. The Haversian or central canal, that's the central channel that contains the blood vessels and the nerves. Osteocytes, osteo means bone, and cyte means cell, so these are the mature bone cells. Lacuna, those are the small cavities in which the osteocytes live. Caniculi, those are little canals that connect the different lacuna to each other in the central canal, so we can get nutrients and waste products move back and forth. So here there's an osteon, Haversian canal, the lamellas, the osteocytes sitting in the lacuna, connected by caniculi. Okay. So osteocytes, here's where we got the different bone cells. So osteocytes are the mature bone cells, and they can be divided into two main types. Osteoblasts are bone-forming cells. Those are the cells that actually produce the collagen fibers and produce the bony matrix that make bone and lay down new bone. Osteoblasts. I remember this like the Big Bang Theory. Big blast created the universe, right? So osteoblasts create the bone. On the other hand, osteoclasts are large cells that reabsorb or break down the bony matrix. Because remember, one of the main functions of bones, and arguably one of the most important functions of bone, is to store various minerals, particularly calcium salts and phosphates, which we need for muscle contraction and nerve transmission. And if we don't have the right balance of calcium in our blood, minute to minute throughout the day, we will die, okay, if it gets too far out of whack. So we are constantly laying down new bone when we have enough calcium in our blood, but when we don't, if we haven't been eating enough in our diet for a while, we literally start to break down our bones to pull out that calcium. And the cells that do that, okay, they have a lot of lysosomes in them, full of digestive enzymes. They'll break down the bone around it. They'll literally dissolve it and put that calcium back in your blood. Those are called osteoclast. Okay, osteoclast, to break it down. All right, mineral salts. Kind of mentioned this before. 65% of the bone by mass is mineral salts, largely calcium phosphates. And that's responsible for the bone hardness and its resistance to compression. It's like the concrete of the bones, like we mentioned before. And then there is the other part of the bone by mass would be the collagen fibers, marrow, and that sort of thing. Okay, and that's going to do it for our macro and microscopic look at the structure of bones themselves, the organ of a bone. Next, we'll get into bone growth and development, how our bones grow from the embryo onwards, and change and develop over the course of our lifetimes. So, hope you guys enjoyed that and learned something, and we'll see you on the flip side. So long.